Hello everyone and welcome back. In this video, we're going to start a new unit called oscillations. If you're following the AP Physics C curriculum, this will be Unit 6. So oscillatory motion exists when an object moves back and forth. So that could be like you have a mass attached to the end of a spring that is oscillating back and forth in a horizontal fashion. Or it could be a mass that's hanging on a spring that's like boinging up and down. It could also be a pendulum bob that has been pulled to the side that is swinging back and forth. So a lot of our examples are going to be about springs and pendulums. There's a special type of oscillatory motion called simple harmonic motion. And simple harmonic motion occurs when the restoring force is directly proportional to the displacement of the object from equilibrium. So if I could say that again, when the restoring force is directly proportional to the displacement, that statement is really Hooke's law. The restoring force is directly proportional to the displacement. But technically, there's a negative in there. We'll come back and talk about that negative in a minute. All right, but before we go into Hooke's law, I need to go off on a small tangent and talk about damping. So damping it's going to be a reduction of amplitude if I graph out my motion, but really it's what occurs in real life over time. So if I have a spring that's boinging back and forth, over time, it's going to go back and forth, back and forth, back and forth, and less and less and less and less, and it's probably eventually going to stop boinging. If I had a mass on a spring that's boinging up and down, it's probably going to eventually stop boinging. And if I graphed that out, like it would go really high, the first boing, and then not as high, then not as high, then not as high, then not as high, and it eventually kind of like just peters out. The same thing could be seen if you had a bouncing ball, where the ball goes up really high after the first bounce, and then not as high, and then not as high, and eventually the ball stops bouncing. In terms of a pendulum, it would be pulled off to the side, and then the pendulum goes like this and goes up at the same height, and then the next time it doesn't go as high, and then it doesn't go as high, and then it doesn't go as high, and eventually the pendulum stops. So that idea of the amplitude decreasing tells us that energy is being lost. The pendulum does not have enough kinetic energy to turn into the same height of potential energy as it did before. And so the energy is lost due to heat or friction. It could be air resistance in terms of friction. It could be heat of the impact of the ball hitting the floor. But the point is that we are going to look at springs that are oscillating, pendulums that are oscillating, and we are going to make the assumption that damping is not occurring. So there is going to be no loss of energy to our system. All right, so with that, we're going to go over here and we're going to look at Hooke's law. So let's talk about what the restoring force is and what the displacement is with respect to equilibrium. So over here, I have a stretched spring. So let's kind of put it back to where it was. So the spring at the start of the story might have been something like this, because the mass needs to be sitting here at x equals 0, which is going to be called equilibrium. And then I'm going to take this mass and I'm going to pull it a distance x. I'm going to stretch it a distance x. So now the mass is over here and the spring is stretched. So when I hold the mass here in the stretched position, there now exists a force in the spring that wants to go back to equilibrium. And so that force in the spring is called the restoring force. So some people think that S refers to the spring, the force in the spring. Some people think the S comes from the S in restoring. But the important thing is to know that I pulled the mass in the positive x direction, and this restoring force that's in the spring wants to make it go back in the negative direction. So this negative sign does not go with the K. That negative sign just means that the left and the right side of the equation are opposite each other. If I pull with positive x, then the restoring force acts in the negative x direction. I could also take this mass and I could compress it. So take it from equilibrium and I could push it this way. That would squish the spring. And so I pushed it in the negative x direction. And now I have a compressed spring. And so I'm holding it, but I know that as soon as I let go, it wants to boing back, and it's going to boing back in the positive x direction. So again, the negative sign shows that the F and the X always act in opposite directions. All right, the next thing that I want to talk about is K. So K stands for the spring constant. So the spring constant sometimes has different names in a problem. I've sometimes seen it referred to as the force constant or the stiffness constant. And let's use the word stiffness here for a minute. I kind of like stiffness constant because it lets you realize that if K is a big number, I'll make it like 10,000. That's a really big stiffness constant. It means that the spring is stiff or not very stretchy. And if I had a K value of 100, that's a smaller stiffness constant, which means that spring is very stretchy, like a slinky is very stretchy. Maybe a slinky has a K value of 1. I don't know. All right, but we should also be able to design a lab in that we have to calculate the spring constant, or we can determine it experimentally. So how could I do that? So here we have a spring that is hanging from, I'll say something. All right, but I'm going to draw it over here. So there's a spring hanging from something. So I'm going to call this spot right here equilibrium. All right, but now I'm going to hang a mass on the spring. So let me write the word mass down here. And I'm just going to take a mass in grams, and maybe I hang a 100-gram mass from that spring. So when I hang the mass from the spring, it's going to stretch. And so if I'm measuring from the bottom of the spring, I can see that it stretched this amount, this vertical amount, and that would be X. So that's the X here. That's called the displacement. And I'm going to write X here because maybe I measure that in centimeters. In the lab, that's probably what I would do. All right, then for the next trial, I'm going to hang a heavier weight. And so we'll call this one, I'm just making up a number, 250 grams. So if I hung a 250, I expect my spring to stretch even more. And so now, if I'm measuring from the bottom of the spring, I am measuring always from equilibrium, because equilibrium is my X equals 0. So measuring from here to here would be how much it stretched with this value over here. All right, so why do I have so many columns going on here? Because if I'm going to find K, I can look at Hooke's law and see that I would like to graph the force on the y-axis and the displacements on the x-axis, and then I would expect my slope to be equal to K. So one of the things is I noticed that my my displacements really should be in meters. So maybe that's why I wanted another column here so that I could convert those into meters. And the masses that I hung down, I need to convert into forces, kind of like weights, like FWs. And so I might take my mass and I might change it into kilograms. So that would be moving my decimal over 3, so like 0.1, 0.25. And then to turn it into a force, I would want this to be in newtons. So I would take my 0.1 times 9.8, and that would be 0.98 newtons. When I'm all done with my data table, I need to graph the forces on the y-axis, the forces in newtons, and the displacements in meters on the x-axis. So these need to be my x values. These need to be my y values when I put them in my calculator or I perform linear regression to do that. So we should be able to find the spring constant of what's called a linear spring. But some springs are not linear, meaning that if I graphed f and x, I would not get a linear relationship. So nonlinear springs might look something like this. You'll notice that the, say, diameter of the coils is not consistent, or the spacing of the coils is not consistent. And so we would have to write the restoring force as a function, and I just made one up here. The restoring force could be equal to negative 1/2 kx squared. But I could still design a lab to collect data like this to find the restoring force of a nonlinear spring. But then I would just have to think ahead a little bit and say, okay, so I have all my data, but since it's a nonlinear spring, I'm going to graph my forces on the y-axis. And it looks like I need to graph x squared on the x-axis. So I'll do y equals mx plus b. Forces on the y, x squared on the x. And then you can see that my slope, the slope of this line, would be equal to 1/2 of k. So I can still use my same procedure to find the spring constant of a nonlinear spring. Okay, on this next page, we're going to look at a graph as a function of time of a mass that's oscillating up and down. So if you can try to picture it this way, what if I had this mass on a spring that's boinging up and down, and let's like tape a red magic marker to the mass. And then I have a piece of paper, and as the mass is going up and down like this, put the marker here over here. As the mass is going up and down, I pull the piece of paper, and you hopefully can see that I'm going to end up mapping out a sine or a cosine type wave that we can analyze. So in terms of analyzing the motion like this, there are some key vocab terms that are very related to each other that I want to introduce in this introductory unit or introductory lesson here. So the first one you already know, it's the period. And the period is capital T, and it's the time for one complete oscillation. So one complete oscillation could be like from where it starts back to where it starts. It could be from a trough of the wave to another trough of the wave. It could be from the, I'll say the x-axis up or down and then back up and back to the x-axis, but a complete oscillation, a complete up and down together. So the time for a complete oscillation is measured in seconds because it's how many seconds does it take for one oscillation. The inverse of that is frequency. And frequency is lowercase f. And if period is the time for one oscillation, frequency is how many oscillations fit in a second. And so I have oscillations over seconds. And since like the number of oscillations is just a count, it means that my only unit is the second, and it's in the denominator. So like 1 over seconds. So period is in seconds. Frequency is in 1 over seconds. In 1 over seconds, we honor Mr. Hertz, and we call those hertz. So we could write this, that period is 1 over frequency. So frequency then is 1 over period as well. We can calculate the period if we could extract it from a graph, but we could also calculate it with the spring equation if we knew the mass that was hanging on the spring and we knew the spring constant value of that spring. All right, and then we're going to introduce a new term today called angular frequency. Angular frequency. And the variable for angular frequency is the Greek letter omega. It's the exact same variable that we used for angular velocity, but it doesn't have anything to do with angular velocity. So it's omega, or we sometimes call it W. And it's basically frequency converted into radians. So instead of the number of oscillations per second, it's the number of radians that pass per second. And so to convert frequency into radians, you end up having to multiply it by 2 pi. So the angular frequency is 2 pi f. And we have that unit because when we start to look at some of the calculus relationships, they are in terms of angular frequency. And oftentimes the trig unit circle is in terms of radians also. And oscillatory motion also applies to circular motion. All right, a couple of quick examples to pull all of this together. All right, so example 1 here, it says a 2 kilogram mass is oscillating on a spring, and it makes 12 oscillations in 10 seconds. So if I'm talking to myself, if I needed to know the period, I can't calculate it with this equation because I don't know K. But I can get it from these facts. If it's period, I know that period is measured in seconds, so I want the seconds to be on top. 10 seconds, and it makes 12 oscillations. When I need to find frequency, I know frequency has seconds on the bottom. So it's going to be 12 oscillations over 10 seconds. And then to get the angular frequency, I can take the frequency and just multiply that by 2 pi. So let me do some quick number crunching here. This one is 0.83 seconds. This one would be 1.2 seconds. 1.2 times 2 times pi is 7.54. And so 7.54, and this is also measured in hertz. All right, now that we know the period, we can use this equation to determine the spring constant. So I'm going to write this down, and I'm also showing you this for a certain reason. All right, so we have 0.83 is the period, 2 pi square root of m over k. Whoops, I forgot to put the m in. The mass here is 2 kilograms. I'm going to throw a 2 right there. All right, so if I have to solve for k, I just want to point out, because of the square root here, maybe the easiest way algebraically to solve this problem is to square both sides. And by squaring both sides, I can get rid of that square root there. So I could have 0.83 squared. I'll square the 2, I'll square the pi, and then, whoops, oh my God, I just drew the square root. Then I will have the mass, which is 2 over k. And I'm assuming k turns out to be 113.7. Okay, the last thing is we should also be able to look at a graph of an oscillating mass that maybe was formed by something like this and extract some information from that graph. So for example, we have a 0.4 kilogram particle that is oscillating up and down in simple harmonic motion. Its displacement, meaning its x value, as a function of time is shown at the right. All right, what is the amplitude of oscillation? So amplitude is measured from equilibrium. So it's like how high up does it go, or it could be considered how far down does it go. So this is 2 centimeters, but I point out that x really should be in meters. So we take that centimeters and convert it to meters. What is the period of oscillation? The period is the time it takes for a complete boing. So I could say that it starts at the top, and how long does it take to get back up to the top? 4 seconds. Other people like to look at an oscillation, and sometimes they like to start at the x-axis and say that I have to have a down, and I got to come up, and I got to go back to the x-axis. And that would be like 1 second to 5 seconds, which would still give me a period of 4 seconds. All right, determine the angular frequency of the motion. Well, if the period is 4, I know that frequency is going to be 1 over the period. So my period is 0.25, and so the angular frequency is going to be 2 pi times 0.25. And so we can number crunch that and get 1.57 hertz. And then determine the spring constant. I think I would go back and use my spring equation to determine the K value. So we know that T is 4, 2 pi. Our mass is 0.4, and then we can solve for K. All right, that's a quick intro of some things that we looked at in the past with a couple of new things added in, and it'll get us started on this unit.